Okay, so we're going to be taking the general equation for angular momentum and applying it to different objects. Okay, so you know that based on the shape of the object, the moment of inertia will vary. So we're going to identify how angular momentum changes based on the shape of the object. And then tomorrow we will go into the conservation of angular momentum. So our first example, we're going to take a look at a pulley. So example 1, we have a 5-kilogram pulley with a radius of 1.5 meters that spins at a rate of 10 radians per second. What is the angular momentum of the pulley? Okay, so we're given the mass and the radius of the pulley, and we're given omega, the rate of rotation, in radians per second, which is the units that we need. We know that the equation for angular momentum, okay, L, is equal to I, the moment of inertia, times omega, the angular velocity. So similar to linear velocity, right, P equals m times v, the rotational equivalent of mass is inertia. The rotational equivalent of velocity is angular velocity, omega. Okay, I varies based on the object's mass and the location of that mass to its axis of rotation. Okay, so if we're looking at a pulley, what shape would we model a pulley as? Hopefully you answered a disc. Okay, so I of a disc, we know is 1/2 mr squared. So we would take that value, 1/2 mr squared, or that expression, okay, and we would plug that expression in for I. And we get that L is 1/2 mr squared times omega. In this example, we have numbers. Hooray! So we're going to plug in the numbers. So we'll plug in for mass, which is 5 kilograms, radius, which is 1.5 meters. Don't forget to square it. And omega is 10 radians per second. So first thing you want to do here, order of operations, make sure you square the 1.5 meters. You get 2.25 meters squared. Now we can multiply straight across. 1/2 times 5 times 2.25 times 10. We get 56.25. Our units, if you all remember, radians are an implicit unit. So we multiply across here, we ignore the radians. They basically disappear, they're implied. So our units for angular momentum are kilogram meters squared over seconds. Right, so that contains 1 more meter in the dimensional analysis of the units, right, compared to the linear momentum. Right, linear momentum's units are kilogram meters per second. Angular momentum is kilogram meters squared over seconds. Okay, and that's because it's rotating about a radius. Okay, so if we have a pulley, we model I as a disc. If we have a stopper on the end of a string rotating above my head, right, we would model that stopper as what object? A point mass or a point particle, right? We use mr squared. What about a bowling ball? So in our next example, we're going to take a look at a bowling ball. And I'm sure right now we all would love to be bowling, okay, instead of inside of our houses. But let's just imagine. So we have a bowling ball that has a mass of 5.5 kilograms and a radius of 12 centimeters. It is released so that it rolls down the alley at a rate of 12 revolutions per second. Find the magnitude of its angular momentum. Okay, so we again know the equation for angular momentum is I times omega. A bowling ball, we'd model the object as A sphere, a solid sphere. Okay, so I for a solid sphere is 2/5 mr squared. So starting with the equation for angular momentum, we would plug in that expression for I. And we would get that L is 2/5 mr squared times omega. Okay, so in our last problem, we just plugged in, right? But we should see an issue here, right? The omega that's given to us, the rate of rotation that's given to us is in revolutions per second. Omega needs to be measured in radians per second. So before we can plug in and solve, we must convert. So we take 12 revolutions per second. We need revolutions to cancel, so we multiply by the ratio 2 pi radians over 1 revolution. The revolutions cancel, and we're left with 24 pi radians per second. Once we have omega in the proper units, we can plug right in. Okay, don't forget that radius must be in meters, so we need to move the decimal place over 2 times. So we have 2/5 times 5.5 kilograms, so it's 1.12 meters squared, times 24 pi radians per second. Okay, so you can leave 24 pi as a decimal, but it's more exact if you leave it in terms of pi until the last step where you multiply across. Okay, so we square 0.12 meters first. We get 0.0144 meters squared, and then we multiply straight across. 2/5 times 5.5 times 0.0144 times 24 times pi. Make sure you put a multiplication sign in between the 24 and the pi. And our answer, our final angular momentum, is 2.39 kilogram meter squared per second. Okay, so in the Google form, there are a few questions that are similar to these two examples, except the objects, the shapes have changed. Okay, you need to find the angular momentum. So please make sure that if you do not have your note card with you, okay, there's an emergency note card, aka Google document in Classroom that you can utilize. Okay, please make sure that you're approximating the shapes correctly. You're going to type those answers in to the Google form. Okay, there's also a question that you're going to have to think about. Maybe you can text or call a friend in class to discuss this one. So if there's no angular momentum, if the object is not rotating, can it still have linear momentum if there's no angular momentum? Okay, and how do you know that? So again, that question is, if the object has no angular momentum, can that object have linear momentum? Yes or no? And how do you know that? Okay, so you can head to Classroom and fill out that Google Doc. If you have any questions, you can add them in the document, or sorry, excuse me, you can add them in the Google form. Okay, there's a spot for questions, or you can come to the Google Hangout today after school from 2:30 to 3:15.